All right, good morning, everyone. Hope you all had a good weekend. Are there any questions before I begin today? Anything you need to clarify? We're all good? You sure? Okay, thank you, Sierra. Okay, so today, properties of functions 3.3. So we are on schedule right now in terms of our calendar, which is amazing because all my other classes we've fallen behind. But we are on schedule. Today we're going to cover 3.3. And then next class, oops, that's not Monday, that's Wednesday. We will cover 3.4, library of functions, can't spell. And the homework for today's class, the homework will be due tomorrow night. So before class next time. And then the 3.4 homework will not be due until Sunday night at 11:59. But remember, Sunday is Super Bowl Sunday. So you might want to take care of that before Sunday. That's totally up to you. And then our first exam is 2 weeks from today. All right. So we'll talk more about that probably next week. All right. And that's it. Okay. I think we're ready to go. So we've got a couple of things to do. I'd like first to start with, this is not a quiz. I'm going to send out a poll. I want you to look at this question here. Let me make it a little bit bigger so you can see it. Okay, I need to fix something here. Oop. Need to put a little bar over that 9 there. All right, so go ahead and read this. Consider a number line. Okay, so think about the number line. I'm asking you, what is the number that is right to the left of the number 1 on the number line? And I'm going to launch a poll and let's just see. You're not going to be graded on this. I just want you to think about, if you had a number line, here's 0, here's 1. I'm asking you, what is the number that is right there next to 1 on the left-hand side of 1? So go ahead and answer what you think. The choices are 0.9. 0.9 with a bar on top means 0.99999 forever, repeated forever. The number 1 itself, or there is no number to the left of 1. We'll just take, I want to see if I can get everyone to respond here. And believe it or not, this is tied into today's class. So this isn't just random stuff here. I need you to really think about this. Okay, that's pretty much everyone. I think we've got maybe one. Oh, there we go. Got everyone. All right, here we go. Let's end the poll. Let's share the results. So we have 35% of you put the first one. We had 47%, almost half of the class. That nobody thought it was 1. And we had 18% say no. There's no number to the left of 1. All right, now I guess I should have said this. It was implied. I'm talking about the number right to the left of 1, right? Right, the one closest to it, but to the left of 1. So, all right, the correct answer here is D, all right? That there is not a number that is directly to the left of 1, all right? Now, I need to explain this to you because this is a very important concept for today's material. And the book doesn't talk about this at all right? But especially like as you move on into calculus and stuff, understanding this is important, all right? About this, it has to do more about our number system. So first of all, let me show you why it's not the first choice, okay? It's not 0.9 because if you look at a number line, here's 1. Let's say this is 0. If I put 0.9 here, I can find a number that's even closer than that, all right? All I'd have to do is pick the number right in the middle of those, okay? And the way that you can find a number right in the middle of 2 numbers is to take their average. Okay, that's how you can do it for any 2 numbers. To find the number right in the middle, you just take the average of the numbers. So if I take these 2 numbers, add them up, 1 plus 0.9, and then divide by 2 because there were two numbers. I get 1.9 divided by 2. And what does that go in there? How many times does that go in there? It'll be, you'll get I think 95, right? 0.95 is what you'll get here. You can do it on your calculator, right? I actually have my calculator today. Yeah. All right. So you get 0.95, right? So that number's even closer. Do y'all agree? Okay. So now what you could do is you could do this again, right? You could say, okay, here's 1 and here's 0.95, right? That was even closer. And now you could do it again. You could take a number right in the middle of that and do it on your calculator. Do the average of those two. So 0.95, add 1, divide by 2. And the number right in the middle of that is going to be 0.975. And here's the thing. I could continue to do this forever. And I'm never going to run out of numbers right in the middle. I'm always going to be able to find a number between the two, no matter how close you get. All right. So why is it? So is everyone convinced it's not A? Right, because I can find a number closer. Now let me explain why it's not C. The reason it's not C is because I'm looking for the number to the left of 1, which means it would have to be different than 1. It couldn't be the number 1 itself. All right. So it can't be 1 because that's the same number. All right. Now B is the one that's very interesting. All right. Now this is going to be hard for me to explain to you. I mean, not hard, but it's going to be weird. Okay, so let's think about that number, 0.999, and it goes forever, right? I just keep doing 9s forever and ever and ever and ever. So, you know, put a bar anywhere I want there. This is a very good answer, and almost half of you picked this, and I like that answer because it seems like that number should be the number that is right to the left of 1, right? It seems reasonable. Well, it turns out that this number is actually not the number right next to 1. This is the number 1 itself. Okay, I'm going to try and convince you of that. And it's going to be weird. This is the first time you've probably ever seen something like this. I'm going to try and show you right now that this is actually equal to 1. Okay, so let me try and convince you. You ready? I'll try and convince you of this. So here's what I'm going to do. I just want you to clear your minds for a second. All right. And I'm going to write some stuff down and you're just going to agree or disagree. All right. So I'm going to say, let X be equal to the number 0.999 forever. So those 9s go forever. All right. Everyone okay with that? I'm going to define X to be that number. Now what I'm going to do is I'm going to say then 10 times X would be, okay, so when you multiply a number by 10, what does it do to the decimal point? Anytime we multiply a number by 10, what happens to the decimal? Go ahead. Anybody? Y'all don't want to talk to me this morning?
It moves to the right.
It moves the decimal point to the right, 1 space, right? So would you all agree that this should be 9.999? And it doesn't matter how many 9s I put here, right? They go forever. Yes? So do y'all agree with that? We're good? 10 times X is 9.9999 forever. Okay, now I want you to think about two completely kind of separate ideas. First of all, if I ask you algebraically to take 10 X's and subtract X, how many X's would you get? If I said 10X, take away 1X, how many X's do you have?
9 X's.
9, right? You have 9 X's. Okay, great. Now, for this problem, 10X was 9.999, right? Forever. And I would like for us to subtract from that 1X. So subtract from that 1X, but 1X was the 0.999 forever, wasn't it? And do you all see that if you subtract these two, these tails, all the 9s cancel each other, all the dot, you know, like 0.999, all those 0.9s that go forever, do you see that they kill each other off when you subtract? And all you're left with is what? That 9 out front, right? So this is 9. So what you're telling me is that 9X must equal 9. And now if you divide both sides by 9, you get X must be 1. But wait a minute, we said X was 0.999 forever. So we started out by saying x was 0.999. We used just algebra to show that x has to be 1, which means that those are the same numbers, which is like, whoa, what? Okay, I mean, that should be like weird. That should be weird. It is. But that's the number that most people think is right next to the number 1. The correct answer here is that there is no number to the left of 1, meaning that there is no closest number. Like as soon as you think you found it, right? If you say, oh, look, hey, look, I found it, here it is. And you tell me, there it is, okay? And you show me the number. As soon as you show me that number and tell me that you think that's the one closest, I will always be able to take the average of that number and 1 and get one that's even closer. And we can always do that. So there, it's like you can go as close to 1 as you ever want to get, but you'll never get to 1. Does that make sense? There's like an infinite number of numbers in there, which is really an important property of our real number system. It's this idea of completeness and denseness. It has this density to it. There's all these numbers in here, infinite number of them. Okay, so why is this important? Why is this important? Well, there's 2 preliminary concepts we need going into today. And we've talked a little bit about this already, but I really want to make sure you understand it. This idea of a closed interval versus an open interval. So when we're looking at a closed interval and we're saying, hey, you know, everything between 0 and 1, including the 2 endpoints, right? Including the 2 endpoints. Then would you all agree that if you're looking at a closed interval, this is the largest number, this is the largest number there, right? The number 1 is the largest number. There is no other number bigger than it. Do you agree? That's the largest number in that set of numbers. And then the 0 is the smallest, right? So 1 is the largest and 0 is the smallest. With me? Right? But if you look at an open interval, right? If you look at an open interval, that's all the numbers between 0 and 1, not including 1 and not including 0. My question to you is, what's the largest number in here? There is none. There's not a largest number. Okay, because again, as soon as you try and tell me what number is largest, if you say, oh, well, 0.99939, you say that's the largest number in there. I'll say, no, I could just add one more 9. And it's even bigger. And then you say, okay, well, that's the biggest one. Well, I'll just add another one. And then you say, that's the biggest. I said, no, I'll just add another 9. And then you'll say, okay, well, then just put a bar on it. Now, and then I'll say, no, you can't put a bar on it, because put a bar on it, that's the number 1. And you're not allowed to have 1 in there. Do y'all see what I'm getting at here? Like, there is no largest number in that open interval. And at the same time, there's no smallest number, because you can't actually get to 0. You can get as close to 0 as you want, but you're never going to get there. All right. What we can say is that the numbers in here between 0 and 1, we can say that they're bounded. Like, we know they never go past 1, and we know they never get smaller than 0, but you cannot tell me that there is a largest number in that set of numbers. And you can't tell me that there's a smallest number in that set of numbers. Does this make sense? It's kind of an abstract idea, but it's a very important concept. Are there any questions over it? So I'll give you kind of another example here. What if we had this? What if we had a function, okay, that started here and went up like this and ended, but I put an open circle right here. And let's say that this is 2 here, and let's say, just for the sake of not having the same number, let's say that's 3 there. Okay. So if we look at this and I tell you, hey, everyone, that's some function f. From what we talked about last class, right? When we talked about last class, the domain of this function, right? The domain would be all the things you can plug in. So we go and we look at this, and we look on the x-axis and we say, oh, okay, well, you can plug in, can you plug in 0 here? Is there a point? If you plug 0 in, it spits out that point 0, right? So 0 can get plugged in. All the numbers in here can get plugged in, but can you actually plug 3 in? No, right? I'm seeing heads shaking. See, 3 can't get plugged in because you have this open circle here, right? So your domain is from 0 to 3, not including 3, right? Not including 3. So I put a parenthesis on the 3 here. That means you can plug in any number you want all the way up to 3, but not 3. So you can plug in 2.9, 2.95, 2.999, 2.99999, right? Can you plug in 2.9 with a bar on top?
No.
No, that's 3. Can't do that, okay? So you can go as close as you want to 3, but you just can't ever let it be 3. Now, at the same time, let's look at the range of this function. The range of this function f are the outputs. So you can see here that we start here at 0, and then we've got about y values that go all the way up to here. But see, we never get to 2, do we? Right? We never get to 2. So the range of this would be everything from 0 to 2, not including 2 because there's a hole there, so you never actually get to 2. With me? So does this function, listen to this question carefully, does this function have a highest value? Is there a value that comes out of this function, the highest it ever gets? Yes or no? What do y'all think? Here, hold on. I'll ask you. I'll do a poll, okay? Question is, yes or no, does this function have a highest value? Yes or no? And if you say yes, you better be able to tell me what it is. So everyone's saying no. Do y'all understand that? Yes? There is no highest value here because that's a circle, but because that's an open circle here, there's no highest value. Good. Now, if I put a solid dot there, if I had filled that in dot, then you close it, and then you can tell me the highest value would be 2. Okay, then you could, all right? All right, that's our first preliminary concept that we need going into today is this idea of open versus closed. By the way, if you have an interval that is, one side of it is got a bracket and one side of it has a parenthesis, you can call that either half closed or half open. If both sides are brackets, it's a closed interval. If both sides are parentheses, it's an open interval. But if you have a mixture of bracket and parenthesis, it's called half open or half closed. It's totally up to you which what you call it. All right.
Quick question.
Yes.
Okay, yeah, so I do remember this. I just wanted to clarify the brackets when it's so when it has a bracket, does that mean that that means it's closed or open?
Closed. The
Closed,
bracket
okay.
means you include that point. You want to include it. The parenthesis means everything up to that number without actually being that number.
Okay, tracking. Okay. Thank you.
Yep. Okay. Yeah, and let's move on. Second preliminary concept is it's separate. It's totally different idea. Okay, so it's preliminary. It's stuff you should have seen before. So this has to do with lines. And we should all be comfortable right now in this class that if somebody gives you 2 points, okay, 2 distinct points, that's all you need to define a line, right? To define a line on a flat sheet of paper, give me 2 different points. There's only one line that goes through both those points, right? Oops, I kind of missed it there, right? There's only one line that goes through those 2 points. And a lot of times we can label, well, a lot of times we label this first point x1, y1, and the second point x2, y2. Right? And then this is our line. What everyone in here needs to kind of be comfortable with right now coming into this class is that if somebody gives you 2 points on a line, you should be able to find 2 different things if I ask you to find them. The first thing is you should be able to find what's called the slope of the line. And I'm sure you've all seen this at some point in your life. The slope, we usually use the letter M, and it is defined to be the rise divided by the run. So this little notation with a little triangle in front of y, this triangle stands for delta. And delta is what we use in physics and in math to represent any sort of change in something. So we're saying the change in y, which is the rise, divided by the change in x, which is the run, the left and right change. So if you take this ratio, rise divided by run, what you're going to do is take the y coordinate here, subtract that y coordinate. Okay, that's this operation. And then you take the x coordinate here and subtract this x coordinate. That's this operation. You figure out what that ratio is. It's some number, and that represents what we call the slope of the line. That all look familiar? Yeah, just nod your heads, yes. Look familiar? Okay. So we need to be comfortable with that. Then after we know the slope of a line, everyone should be able to find the equation of the line. Now, those are two different things. The slope of the line just gives you the pitch of the line. The equation of the line is actually the algebraic representation of the entire line. So we use a formula. This is something that you should have seen in some previous class. This is what's called the point slope formula for a line. And what it is just a formula where all you're going to do is you're going to plug in x1, you're going to plug that point in here, you're going to plug y1 right here, and then whatever your slope is, I'm running out of colors. Whatever your slope is gets plugged in right there, and then you have this new equation of a line. I'm going to do an example, all right, just to make sure we're all okay with this. So this example says, all right, find the equation. I'm asking for the equation of the line through these 2 points. So I give you 2 points, and I want the equation of the line. So what we're going to have to do is first find the slope. After we find the slope, we'll use this point slope formula to find the equation. So first things first, I'm going to label these. I'm going to call it x1, y1, and this one x2, y2. By the way, if you decide to label it opposite of me, if you did x1, y1 on this one on the right and x2, y2 on the left, we would get the same answer. We should get the exact same answer. All right. That's the way I'm going to do it, though. So first, the slope. So the slope is going to be the y2 minus y1 over x2 minus x1. So y2, I take -4. I subtract from it y1, which is 1. I divide that by x2, which is 5, and subtract from it. Be careful here. We're subtracting x1, but x1 is -1. So we're subtracting a negative. So the top becomes -5, and the bottom becomes actually +6, because you're going to do 5 plus 1, so 5/6. This is the slope of the line, right? That's the slope. And hopefully you know this from the past also, that when you talk about slopes of lines, a positive slope means it looks like this. This is a positive slope. And a negative slope, it looks like that, negative slope. So if you look at it like reading a book from left to right, a positive slope means you're like going up, and a negative slope would be like you're going down, like a roller coaster, right? Up or down. Okay, now that we have the slope, all I'm going to do is use this formula right here. I'm going to do this right here. So for the equation, I'm going to use this formula, y minus y1 equals m times x minus x1. We're going to need this formula, and you're going to need this formula a lot in calculus. So I'm going to say y minus, now y1 was 1, equals m, which is the slope, -5/6, parentheses x minus, and then x1 was -1. So we get y minus 1 equals -5/6 x plus 1. And that is the equation of the line. You can move things around, like you could add 1 to both sides, you could distribute that through. I'm not going to, I'm just going to leave it like this, because that is an equation of a line. And I'm just going to show you that this actually did work. So let me see here. -1, 1, 5, -4. So first thing I'm going to do here, -1, 1. I'm going to have the computer plot me the point -1, 1. Let's go ahead and label it. There's -1, 1. And the other one was what, 4, -5? All right. There it is there, label it. Okay, so we were given those 2 points, right? And,
It was 5, -4.
oh, was it? Okay, thank you. 5, -4. I would have found that out in just a moment. All right, so here we go. We've got these 2 points, right? And we were trying to come up with the equation of the line that went through those 2 points. So now I'm going to type the equation in. It was y minus 1 equals -5/6, and then it was x plus 1. There it is. Look at that. So we found the equation of the line that goes through those 2 points. We all good with that? All right. You sure? You sure? We're good? All right, that's it. Those are the preliminary concepts. I'll be using those now as we go through the material for today. Here we go. All right, lots of definitions. Did I make a folder for y'all with the notes for the class? I forgot if I did. Does that sound familiar or no?
I don't think so.
Let me
Yeah, I
see
don't think
something.
so either.
Let me see something real quick. I think I made the folder, but I don't know if I actually. Yeah, I haven't done that. I think that's a good idea. So what I'm going to do here, 1414 Zoom notes. And share this folder. Sorry to take time out of class for this, but copy that. Okay. This take me a minute. I'm going to email everyone this right now. So what this is, I write on, everything I'm writing on my screen. You can always go back and watch the video, but if you just want like a PDF copy to just look at the notes that I write, that's what this will be. So let me just email the class real quick. Okay, Zoom notes link. There we go. Okay, I've sent that to you. And then now what I'll do is when we're done with class, like here's last classes. I'll take this and I'll save it to that folder. And you can just go upload it or download it if you want. Make sense? That way, when you're looking at these notes, you don't have to sit here and copy all this down. It's not about you regurgitating this. You just pay attention to what it's saying. All right, so 3.3, properties of functions. So when it comes to functions, which we talked about last time, there's a bunch of different properties and aspects of the functions that we need to be comfortable with as we move into, well, this class, but also into calculus and pre-cal. The first property of functions is something called even and odd. Okay, a function, if you give me any function, it's either going to be an even function, an odd function, or neither. Okay, so it's kind of like there's 3 possibilities: even, odd, or neither. That's it. Even and odd is kind of a very special property. So this is where we define what it means to be even and what it means to be odd. So first of all, what does it mean to be even? Well, here's what it means to be even. And when you look at that, you're like, okay, what the hell does that mean? All this means is that when you plug, the way I look at it at least, is this means that if you plug x into the function, okay, plug in some value, I don't care what it is, you get the same answer it's equal to, right? So you get the same answer if you plug negative x in. So it doesn't matter if you plug in the positive or a negative of a number, you're going to get the same result. So here's an example. All right, I'm going to give you an example over here of an even function. F of x equals x squared. I'm going to give you like the most generic even function I can think of. All right, so think about this function. It is an even function. Let's see why. If I plug in 2, I get the same answer as plugging in -2. Do you agree? Plug in 2 squared, I get 4. Plug in -2 squared, I get 4, right? Check. And wouldn't that work for any number that I plug in? Plug in 3, plug in -3, check. It's the same, right? 3 squared is 9, -3 squared is 9. What about 0? What if I plug in 0? Will it work for 0? If I plug in 0 and then plug in -0, wait a minute, -0 is still 0, isn't it? So that would still give you the same answer. And that will work for any number you ever pick. So this is an example of an even function. And it's kind of a dead giveaway. Look at the power on x. Do you see it's an even number? That's like a dead giveaway that this is an even function, is the fact that that power is even. Now, an odd function is different than that. An odd function is well, it's kind of hard to understand this algebraically. What it's saying is, in order for these two to be equal, okay, in order for these two to be equal, I'm going to plug some number in and get an answer, but then I have to change its sign, and then it will match what I get over here. Okay, so let me give you an example of this one. So as an example here, if a generic example would be x cubed, all right? So let's check to see what happens. If I plug in 3, let's just plug in 3, what happens? Is it equal, my question is it equal to plugging in -3? Is that the same? Plug in 3, what do you get when you plug in 3? Should I call on people today? I should, right? Sierra, are you there?
Yeah, I'm here.
Okay, Sierra. Okay, so what happens when I plug 3 into this, Sierra?
3 into that function.
Into this function. So you're doing 3 times 3 times 3, right?
Is that 81?
Too much. 27.
27, yeah,
27.
sorry.
That's all right. It's Monday. Okay, my question is, does that equal what you get when you plug in -3?
Yes, it does. Or
Well,
no,
No, right? They'll be off by a sign, won't they? Like this
Yeah,
one will be
negative.
-27. And so they're not equal, right? They're not
No,
equal
they're not.
unless you had put a negative out in front of this, right? If you put a negative in front, then they're the same, right?
correct.
That's exactly what this is saying here in the middle. It's saying if you plug in a negative number, you will get the same thing as the original function, but you have to slap a negative out front. You see that? That negative right there is what we had to put in front of that 27 in order to make it match. We didn't have to do that for an even function. For an even function is that, you know, you get the same answer regardless if you plug in a positive or negative. With an odd, you have to change the sign in order to make a match. Okay? We're going to get more practice with this. It's just to get you thinking about it. Now, we want to know what these things look like geometrically. So this next note says a function is even, okay, if and only if its graph is symmetric with respect to the y-axis. Symmetric with respect to the y-axis. What does that mean? And then it says it's odd if and only if the graph is symmetric with respect to the origin. We talked about this at the end of class last time. So I've got 3 pictures here of 3 different graphs. And I'm going to talk about which of these is even, which of these is odd, and which of these is neither even nor odd. So look at the first one. Do you all agree that if you take the right side of this graph, reflect it over this y-axis, it's a mirror image of itself and it would land on top of itself. And so it would be symmetric to the y-axis, mirror image, right?
Yeah,
So this is what type of function? If we have
Symmetrical.
y-axis, I'm sorry?
symmetrical.
It is symmetric, but is it even or odd?
Even.
Even, I heard someone say even, yes? It's even because it's symmetric to the y-axis, right? Y-axis. So this is even. Okay, it's even. All right, how about, is it Malak? 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 No?
Yes.
Malak, how are you doing?
I'm okay. How are you?
Doing good, doing good. What do you think of the second one? Do you think the second one is even, odd, or neither? Well, let me ask you this, is it even? If I take the right side of it, like this side, and imagine reflecting that over the y-axis, would it land right on top of itself?
No.
No, right? It would look like this, right? And that's not what we have, right? So it can't be even, right? So it's not even. Not even. All right. Now, odd means you're symmetric to the origin. Now, y'all remember I told y'all what that was at the end of class last time? Or no? No?
Can you explain that? Because I had a doctor's appointment that day.
Yeah, symmetric with respect to the origin means it's a reflection over the y-axis and then the x-axis, a double reflection. So let's take this and reflect it over the y-axis first, right? It would go like that. We know that it's not that. But now take that dotted part and reflect it over the x-axis. And if we do that, it would look like this. Do y'all see that? It's a double reflection over y, then over x. Is that black part landing on top of this blue part?
No.
No, right? It's not. So it's not odd either. Which means it is neither.
Neither.
And how about this last one? Let's see. Diego, you here?
Yes, sir.
Okay, what do you think about this last one, Diego?
It's an odd function.
It's an odd. Okay, so good. You see, if you take the right side of this, right, reflect it over the y-axis first, it's going to look like this, right? And then reflect that over the x-axis. And when you reflect it, it will come down here and it will land right on top of itself, right there like that, which makes it odd. Now, just to show you the functions that I had put up there, I said generic examples. I showed you x squared was an example of an even, and I showed you x cubed was an example of an odd. Let me get rid of these other things here. So let's talk about y. Here's x squared, right? Everyone agree that's even? Reflection over the y-axis, okay? And then the x cubed is odd because you would do a double reflection. So you'd go here first, right? That's not very good. And then reflect it over the y and it would come down here. It would land on top. Okay. So when you have a double reflection, that's called reflection over the origin. It's kind of a weird name, reflection over the origin, to be like a double reflection, but that's what it is. That's what we call it. Okay, that's the first concept in terms of properties of functions. You've got either even or odd. And would you all agree that if I give you a graph, it's somewhat easy to tell which it is, right? Somewhat. The hard part is if I give you the function algebraically and ask you if it's even or odd. That's what's hard. Okay, so let's do that. Here I have 4 different functions and I'm asking, is it odd, or sorry, is it even, odd, or neither? All right. So I'm going to do the first part, A. Here's the function. And here's the way I recommend you do this. You're going to just find 2 things. First thing you're going to find is just f of x, all right, which in this case is just x squared minus 5, okay? The next thing that you should find is f of negative x. And that means instead of plugging x into this function, I'd like for you to plug negative x in. So that means you're going to take the negative x and square it and subtract 5. See the subtle difference between these two? In the first one, you're just plugging x in, which just means the original function. And in the second one, you're plugging a negative x in, which means you've got to take the negative x and square it. But Ashley, are you there? I think I see Ashley, but I don't hear Ashley.
Hello?
Hi, how are you doing, Ashley?
Hi.
Doing okay?
Yes, you?
Yeah, I'm doing good, doing good. Ashley, my question is, if I take a negative value, like negative x, and square it, it would have to turn out to be what?
Positive.
Positive, right? So this, we know, is the exact same thing as doing just x squared minus 5, right?
Yes.
Okay, so Ashley, what we've done is we've said, what happens when you plug in x, and we've got an answer. And then we said, what happens when you plug in negative x, and we have another answer, right?
Mhm.
To check if they're, to check to see if this is an even function, okay, what you're gonna do is ask yourself, are these the same or not?
Mm.
So are they? Is x squared minus 5 the same as x squared minus 5?
Yes.
Yeah, right? So that means they're even, it's an even function. Got it?
Yes.
Okay. Now, had they not been the same, we would do something else, but that's the first thing you always do with a problem. And hopefully it's even. If it's not, you have to proceed. So let's go to part B, all right? And remember, I told you, a function can be even, odd, or neither. You cannot be even and odd at the same time, okay? It's even or odd or neither, 3 possibilities. So now we're gonna move on to B. G of x is x cubed minus 1. Okay, so here we go. First thing I'm gonna do is I'm gonna plug in x, which doesn't do anything. It's the original function, all right? The next thing I'm gonna do is plug negative x in. So that's gonna put a negative x in here, and we're gonna cube it and then subtract 1. So let's see, I'm gonna try and get through people today. I'm trying to call some people I haven't called on in a while. How about Gloria? You there? Gloria. No. Okay. Isabella.
Yeah.
You there?
Can you hear me?
How you doing?
Good. How are you?
I'm okay. I'm okay. All right. So my question, Isabella, is if we take a negative value like negative x and we cube it, is it going to become positive or stay negative?
Would it stay negative?
Stay negative, right? So this is really the same as negative x cubed minus 1. Do you agree?
Yes, sir.
Okay. So now I ask you, Isabella, are those two the same?
No.
They're not, right? So right now, these, you check these, are they the same?
No.
No, right? So that means you can tell me it's not even, right?
Yes.
Not even, for sure, it's not even. Now, the next question would be, is it odd, right? Is it odd? Well, to see if it's odd, all you have to do to check if it's odd is take the first one, okay? Okay, this will be the third thing we're going to do. We're going to take the first one and we're going to put a negative in front of it. So this goes back to like when we were doing that problem with 27 and negative 27, we had to put a negative in front to see if they match or to make them match. I want us to put a negative in front of that g function. So we put a negative in front there. You'll see what I did there. I took the g function, which is everything in this yellow box, which is here, and I just slapped a negative number in front. So we're going to stick with Isabella here. Isabella, if I distribute that negative through, what am I going to get? If you take that negative and distribute it through the parentheses, what would you have?
You'd still have a negative, but you would have a positive 1.
Yeah, but you would have a plus 1, right? So you still have negative x cubed, but now you have plus 1. Now what I want you to do, Isabella, is tell me, are these the same?
No.
No, right? Those are not, I can't spell same today. Same? No. And what that tells you is that it's not odd. All right? Those two would have to be the same in order for this to be an odd function. So that means you've eliminated the two of the possibilities. That means it can only be the last possibility. So it's neither, right? Isabella, did that make sense?
Yes, sir.
Okay. Everyone else good? All right. I would like for you to try the next two. All right. On your own. I'm going to give you a few minutes. I'll just restate what you're doing. First, you write the function down, then you plug in negative. You see if those are the same. If those are the same, you're even and you're done. If they're not, then what you're going to do is take the original function, put a negative in front of it, and then check to see if the second one and third one you get here are the same. If they're the same, then you're odd. If they're not, then you're neither. All right. Take a few minutes. I'm going to relaunch the poll. And just tell me when you're done. Just click yes when you've got both of these done. And on part D, those bars next to the X are an absolute value. So hopefully you know what that is. We've got about half of you done right now. We're just going to go 30 seconds. Okay. So you should have gotten that C is odd and that D is even. So I left the work here. Like I said, you can go back and look at this. Are there any questions on that? Plugging the negative in to this one, you have to be a little careful here with the negative x cubed. It gives you a negative x and you pull the negative out front. And then this minus negative becomes plus. And so these two don't match, right? The yellow and the blue don't match each other. But when you put a negative in front of the original function, these two do match. So it's odd. And then on the other one, when you plug a negative into the absolute value always kills off the negative anyway. So you just get x, absolute value of x. So it's an even function. While you were doing that, where the heck is it? I graphed these just to show you. These are all the problems we just did, all four of them. So here was x squared minus 5. You can tell that's an even function because it's a reflection over the y-axis. The second one we did together, x cubed minus 1. You can see here, this almost looks odd, but it's not. Because if you take this left side over here, the right side, and you reflect it over the x-axis, you get this. But here's the tricky part. If you reflect this over the y-axis now, this part that's on the bottom comes up. And so you get something like hold on. Yeah, it looks something like this instead. It doesn't land completely on top. And then the third one, which you did on your own, this is this one. Let me take that one out of here and clear that. That is odd. Because if you reflect this piece over the x, you get this. And then over the y, the bottom part comes up top and the part that's up here on top left comes down. So you get your double reflection. And then the last one is the absolute value function, which looks like a V. And you can tell that that V is a reflection over the y-axis. So that's just to show you visually. Are there any questions on that? Even, odd, we're good, we can move on. Okay. All right, the next concept has to do with, again, these are properties of functions. When you look at a function can be increasing, decreasing, or constant. Now, when we talk about increasing, decreasing, constant, we want to think about when you look at a function visually, think about it as if you're reading a book from left to right, okay? If you read a book from left to right, that's where we come up with these ideas of increasing and decreasing. And I have kind of a little bit of an animation here to show you. Okay, This is an example of a function that is increasing. So what I want you to pay attention to is that if I pick two values of x, okay, here's my first x, I'm gonna call it x1, and I pick a second value of x, call it x2, notice that the second point, this red point, is always higher than this left point. The right point here is always above the one on the left. And it doesn't matter where I am on the function, that point on the right is always going to be higher than the point on the left. Do you all see that? The point on the right is always higher than the point on the left. As we move from left to right, though, notice moving from left to right, it's like if this were, again, like a roller coaster, it would be like you're going up all the time, right? You're just increasing, 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 increasing. So the definition of increasing is a little weird when you look at it. I'm going to show you the definition here. The definition says, if you choose 2 points, x1 and x2, where x1 is to the left of x2. So I'm going to try and show you this visually. If you pick me 2 points, here's x1, and it's smaller than x2, so to the left of x2, then what we have to have in order to be increasing is that the function's value at x1 has to be smaller than the value at x2. So whatever value this pops out, however high that is, we call it f of x1, that must be below the other point over here, f of x2. And as long as that's always happening, then your function is going to be going up as you go from left to right. Questions on that? To be decreasing is the opposite. You pick 2 points, one of them to the left of the other, but now the one on the left is bigger than the one on the right. So I'll show you that visually. Here's an example of a function that's decreasing. So notice if I pick two values, one to the left, one to the right, the one on the left now is bigger than the one on the right. And that's always happening here. So we get a function that is decreasing. So moving from left to right, the function is going down. Okay. Then the last concept is what we call a constant function. So that was increasing, this is decreasing. Constant means that no matter where you pick, the values are equal. So that would mean it looks like this. Pick any 2 points, okay? Pick 2 points, plug them into the function. Notice that it always stays flat. They're not, the right one's not above the left one, the left one's not above the right one. They're both the same the whole time. Then you're going to have what's called a constant function, which is basically just a flat horizontal line. Okay, those are the 3 things that we have in terms of properties of functions. You either have some increasing happening or decreasing happening or some flattening out, constant. So what we want to be able to do, and I should probably say this to start, you know how we just did even and odd, we had a way of figuring out if the function was even or odd. We could do it both visually and algebraically, right? For even and odd, we did it algebraically. We did it visually. When it comes to increasing and decreasing and constant in this class, college algebra, we will only ever be able to tell visually. There's not a way in college algebra to tell if a function is increasing or decreasing algebraically. And actually, that's what you do in Cal 1. In Cal 1, you figure out how can you look at a function algebraically and be able to tell me when it's going up and when it's going down. Okay, that's beyond this class. So all we need to be able to do is look visually. So here's an example. And the question here is for us to figure out by looking at this function. Oh, by the way, is this a function? How can I tell if it's a function? There's a quick test I can do, right? Vertical line test, right? So this is a function. My question to you is, where is it going up? Where is it increasing? Where is it going down, decreasing? And where is it constant? And when I say where, I mean where within the domain. So let's talk about increasing first. Increasing, all right, let's talk about that, increasing. Let's talk about where it's increasing. And let me ask somebody. You better ask someone. All right, Raquel? You there?
Yes.
Increase, decrease, visually understand the idea?
Mhm.
Okay, so on this function, can you kind of tell where it's increasing? Is there any way you can kind of describe to me when it's going up, when it's going down? Or sorry, just when it's going up, sorry.
It's going up around the -2, 0 point.
-2, 0. Okay, so like you're saying around right here,
Mhm.
so like right here, like in this area right here, it's going up?
Yeah.
Yeah, does everyone agree that that is where it's going up? Now, Raquel, do you also notice that it's also going up right here? So like,
Yes.
again, if you were like on a little roller coaster here, you would be going up and up and up and up and up, right? Like this. So on that entire yellow region, we're going up, right, Raquel?
Yes.
So when the question asks where, where is this function f increasing, what they want you to tell me is the x values where it's going up. So what I would do, Raquel, is I would look at this yellow region. I'd look at the far left point here. I would go up to the x-axis and figure out what x value that is. So can you tell what it is?
-4.
-4, right? -4 is where it starts. And then it's going to stop when it gets to this right end point. And what's the x value here?
Which one
X.
was it? You said to the right.
Yeah, I went to the far right where that dot is up at top, right? That's where
Oh,
the
it's
yellow
0.
region is. So 0, right? So from -4 to 0, right, Raquel?
Yes.
From -4 to 0. So here's the way we're going to put our answer. -4, comma 0, like an interval. And whenever you're dealing with increasing and decreasing, I would say just always put open parentheses. All right. Just always put open parentheses. Technically, in this problem, we could do closed, but it's not incorrect to leave it open. Right. So open is safer. So just do that. That makes sense, Raquel?
Yes.
Okay. Everyone else, that makes sense? When you're asked, or when you're being asked to find where a function is increasing and decreasing, you figure out where it's going, or sorry, let's say increasing. You figure out where it's going up, and then you pick out the left x value and the right x value where it starts and stops. It's almost like a domain. And then that's your answer. So how about decreasing? Let's move on. Thank you, Raquel. For decreasing, where is f decreasing? This one's a little bit trickier. Question mark, question mark. Let's see who we got. Zane, is Zane here?
Yes.
How's it going, Zane?
Good. And you?
It's going good, I guess. Okay. So can you tell me where it's going down?
It's going down a -6, -4, and then that 3 and 6.
Good. So you're noticing here in this green region, and then also over here in that green region. And you said it exactly right. It's the x value where it's starting here was -6, and where it stopped was at -4, which is where Raquel had started the increasing, right? But that's where you're stopping the decreasing. So we could say -6 to -4. And then you also said from where to where?
3 to 6.
3 to 6. So it starts here at 3 and it ends here at 6. And so we'll go parenthesis 3 to 6, close it. And then Zane, whenever we have two intervals in our answer, what's that symbol we usually put in the middle of them?
Union.
Union, right? So we put a little U here in the middle. All right. Any questions? One last thing. Constant. So where is it constant? Let's go with trying to pick people I didn't pick last time. So let's go Henry. I didn't see Henry here today. Usually Henry's here with his phone on, or with his camera on. Okay, that's fine. Alyssa. Alyssa. Javier? Jose?
Yes, sir.
Okay, I haven't called on you, right?
No, no, you haven't.
All right, Jose. Do you see where our function is constant?
Yes, it will be 0,4 to 3,4.
So you said okay, so you said 0,4 to 3,4. So yes, I agree. It's between these 2 points. But in terms of your answer, you're always going to give me just the X values, right? Where the starts at the left and ends at the right. So what would you
So
put here?
it will be 0,3.
0 to 3. Okay, 0 to 3. That's it. So just remember, all these values, these are X's that we're putting in here. These are your X's where it's happening, right? X is where it's happening. Any questions? I have one for you. I have one I'm just going to make up on my own here. How about this one here? This is not a trick question, but I'm gonna copy this graph and put it on our notes. Here we go. So I'd like to have the same questions answered here. So where is this graph? Increasing, decreasing, and constant. So I will start here with, let's see, Jose just went. How about Lizeth? Increasing.
Increasing.
And by the way, these are arrows. So the graph goes down, keeps going down, and keeps going up. So if this was a roller coaster, right, Lizette, you were riding this roller coaster. What's happening?
Well, I know that it's like increasing like on the right side. Wait, no, just kidding.
No, you're right. On the right side, it's going up, right? It's up, it's going up, it's going up, it's going up, it's going up, right? You'd be going up on this side, yes?
Yeah.
But remember, you're always reading this like a book from left to right. Okay. So if you were to pick a point like over here, and this was you,
And then it would also be increasing there.
Yeah, you're increasing over here, right? Now, just for a moment here, this is the part that makes it tricky. Just for a moment, it looks like you flatten out, right? Just for a moment. When it comes to being constant, you have to be constant on an interval. To say it's ever constant, you have to be on an interval flat. Here, at the most, we're maybe constant at one point. So that doesn't count. We would still consider this to be increasing the whole time. It's a little weird little subtlety about increasing, decreasing, and constant. You need it to be on an interval. So you're going to be, if you're moving from left to right, you're going up, 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 up all the time. Yeah, you flatten out for just an instant, but you keep going up, 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 up.
So would it be like negative infinity to infinity?
Exactly. Negative infinity to infinity. Yep. You're always increasing. Okay. Now, the reason that there's a couple of reasons this is tricky. All right, because I'm curious to know if I ask you where it's decreasing, not you, Lizeth, but just the whole class. What would you tell me? Are you ever decreasing? Are you ever going down? Not if you're moving from left to right, right? Not if you're reading this like a book. You're never going to be going down, all right? You're always going to be moving up from the bottom left corner to the top right corner. You're always moving up. So you're never decreasing, right? Never. How do you say that though? How do you say there's no answer here? Anyone know? We know that what Lizeth gave us was like everything, right? That's all real numbers. That's everything. How do you say nothing? Well, that's why I gave you this example. I wanted to show you. You do this, okay? That's the symbol we use. This is called the empty set. Now, what I want you to understand about the empty set is that If any of you have a military background, that is what you do whenever you want to write the number 0, so that you don't mistake it with the letter O. But that's military. In mathematics, that means something completely different. That means the empty set. So the way I think, the best way I think you could kind of think about this is, okay, here we go. Here's my trash can. I know I have a small video, you probably can't see it, but I have my empty trash can. I got a couple of things in there. Okay, so right here, Lizette gave us an answer for increasing, and what her answer was a set, okay? So this container that has all the numbers in it, okay? That's Lizette's answer, everything, negative infinity to infinity. When you write a 0 with a slash through it, what it is an empty basket. It's a basket that has nothing in it, the empty set. It's the set that contains nothing. That is different than the number 0. The number 0 is a number. We're not talking about numbers here, we're talking about sets of numbers. Do you see kind of what I mean by the difference between us? It's like a cat and a dog. These aren't the same things. Numbers are numbers, sets are something else. So that symbol, the 0 there with the slash through it, is the empty set, all right? Okay, and then what about constant? Is it ever constant? Well, I said already, to be constant, you have to have an interval, and we don't have an interval where it flattens out, so this would also be empty set. I do not believe that this book talks about empty set. I could be wrong. When you do your online homework, I forget what it says, but you'll find out. What the heck is this? All right, questions? So for increase, decrease, in this class, we will only be looking at this visually and then identifying the intervals. Next concept, local maximums and minimums. So when it comes to, right now what we know is, we talked about even and odd, and that has to do with reflections. The increase and decrease had to do with where your function's going up and where it's going down and where it might flatten out. This idea of a local maximum or local minimum, the way that I like to think about it is like finding like points where you have the king of the hill and the king of the bottom of the valley. So what I mean by that is, if you give me a function, let's say, and let's say it has a bunch of like undulations on it like this. Let's say it does something like that. We will study a function like this later this semester. It's called a polynomial function. And you'll notice that there's a bunch of places where it goes up and a bunch of places where it goes down, right? So like you could say like from here to here, it would be increasing. Here to here, it's increasing. From here to here, it's increasing, right? So everything in yellow is where our function is increasing. I'm gonna put an up arrow. Does that make sense? Instead of me writing the word increasing. So everything in yellow is where my function is increasing. Everywhere in blue is where my function is decreasing, right? And notice that I have these important points. This point right here, this point right here, this point right here, and this point right here. These 2 points, this one and this one, are like little mountaintops, right? And those mountaintops are what we call local maximums. In this particular example, I have 2 of them, right? I have 2 kind of peaks. Now, this point here, okay, is not the highest point on the whole graph, right? Because look to the right side. You see how the arrow keeps going forever? I'm not saying that this is the biggest value, right? I'm not saying that this point here is the biggest value on the whole function. I'm just saying that locally, it's the king of the mountain over there. Like it's the highest point in that little neighborhood. So, you may be like the best basketball player in your group of friends, right? Like that's you. You're the king of the mountain right there, but you're not the king of all mountains, right? There's other people who are better than you. So that's what locals are about. They're about what's happening in this little region. So we have a local max here. We have another local maximum here. And then we have a couple of points that are like lowest points, right? And these would be what we call local minimums. Does that make sense visually? Local max, local min, any high points and low points on the graph would be local maximums or minimums. They are also called, you'll see this in different textbooks, These are sometimes called local extremum. I think I spelled that right. Extremum. Local extremes, local extremum, local maximums, local minimums. It's synonymous. They're all the same. All right. So let's get back to the definition. Let me move this up. Let me get back to the definition. Okay, so what does it mean to be a local maximum? To be a local maximum means that you are at some point C where the function's value at that point C is bigger than or equal to all the other points around it for some interval near it. Okay, that's a crazy definition. Okay, so back to my picture, what we're saying here is that to be a local maximum, you go to some point C, and we notice that the height of that point, right, f of C, is bigger than all these points around it. Okay, you pick any little values around this C and plug them in, they will be smaller. All right. So reading the definition is kind of visually, it's pretty simple. It's just the top of the hill. And then over here, you have, same idea, except it's the lowest point in that little neighborhood. All right. Yeah, local minimum value, same thing. All right. So let's see here. This is an example. Part A. They give you a graph. Is this graph big enough? Can you all see that? All right. Let me make it a little bigger here. All right. So the first question is, at what values of X? Okay. So at what numbers X does F have a local maximum? Okay, so first it's saying, where does it have any local maximums? What X value? And let's see what, Sana, you there?
Yes.
I'm saying that correctly?
Yes.
Okay. So Sana, can you tell me at what X numbers we have a local maximum?
I'm sorry, what was it? I couldn't hear you.
Okay, so the question is, looking at this graph, at what X values do you have a local maximum? What X values?
At 1.
Yeah, at 1. See, at 1, that's where we have a max, right?
Mhm.
So for part A, at X equals 1, are there any other places where you see a local maximum, Sana? King of the Hill. Do you see any other King of the Hills?
No.
No, right? So that's the only one. Now, the second part to this, Sana, says list the local maximum values. So that means it wants to know at that hilltop you're talking about, what's the value that comes out? How high is that point? So can you tell me how high it is?
2.
2, right? The value is equal to 2. Understand, everyone? It's like you're looking at that point 1, 2, and you're saying, oh, it happens at 1. That's where I have the maximum, local maximum. And the value of the function there is 2. We all understand? Any questions? Okay, very good, Sana. Moving along here. Zachary, you there? You understanding?
Yeah, I was just writing it down.
Sure, sure. I'm going to let you have part B. And it's basically the same question, but it wants you to look at minimum values. So at what values of X do we have minimums at?
Well, we have 1 at -1 and we have 1 at 3.
Yes, everyone see that? At 1 and 3, we have minimum values. And can you tell me now the value, those minimum values that correspond to those points?
So the first one, the -1 would, the value would be 1.
Okay.
And then the second one where it's at 3, it'd be 0.
0, good. So you're almost looking at these as like an ordered pair, right? Like this point is the point -1, 1, and this point is the point 3, 0. So when you're giving me where it's happening, you're giving me the X coordinates, and you're giving me the values, you give me the Y coordinates, right? That's basically what's happening here. Questions? All right, C is gonna be for Caitlin. Is Caitlin here?
I'm here.
Okay, how's it going, Caitlin?
I'm good.
Are you understanding?
Yeah.
Mhm. All right, so for part C, shifting gears here back to what we just talked about before this idea of local max and min, wants to know first where the function is increasing. So can you tell where it's going up?
At -1 and 1.
-1 to 1. Anywhere else?
At 3
3 to when?
to infinity.
To forever, yeah. So we're going to say -1 to 1, union, and then you said 3 to forever, infinity. And just remember, these are x's, right? That you're giving me? Very good. Okay, Dominic. You get the decreasing.
Hello, can you hear me?
Say again?
Is that mission? My mic is working.
I can hear you.
All right, perfect. Decreasing, well, would it be considered from going from the, I guess, negative infinity to the 1?
Yes, exactly. So it goes to the left, right? To the left, it's always going up. But if you were to be traveling down that graph, you'd be coming down. So negative infinity to where?
To would it be the 1? Or is it a -1 or a +1?
-1. It'd be -1. So you're always going to pick the x value.
Okay, yeah, sorry.
And then where else?
And then from +1 and then down to 3.
1 to 3. And we'll just throw a union between them.
Yes, sir.
Okay, there we go. This is where f was decreasing. This is where f was increasing. This all makes sense? All right. Like I said earlier, in Calculus 1, our main objective in the class is to be able to figure out where this is happening. It takes a long time to get to it. In fact, this idea of increasing, these are my notes for my Cal 1 class. I have very formal notes for Cal 1. And this is actually chapter 4, section 1 is where we start talking about maximums and minimums. And that's chapter 4. In Cal 1, we actually start in chapter 1. So we go chapter 1, chapter 2, chapter 3, and then we finally get to chapter 4. And that's where we start talking about how you can find these maximums and minimums. And there's a whole set of things you have to learn before you get to it. But it seems like it might be easy. It's very difficult in general to do. So, but just to kind of give you like some, like, I guess something to kind of help you see why this would be important, right? To be able to find maximums and minimums is, you know, if you have a company, right? And you're looking at, you know, maybe this is time and maybe this is your profit, right? Something like that. And you're just kind of analyzing things. And, you know, one thing you might want to know is like anywhere where you had decrease in profit, or maybe you want to know when you had some increases, right? So when was that happening? That's good, right? Because you've got increase in profit, and you want to know also where that's happening, because that's not good, right? So maybe you go and you figure out what this point is, and that's hard to do in general. If someone just hands you a function, it's hard to find those peaks and valleys are not easy to find without calculus. So we want to be able to do that, right? We go and we figure out, oh, well, you know, that's when we hired Robert, right? And all of a sudden our profit started dropping, right? So you go fire Robert. All right, let's get back to business here. How are we doing on time? 25. Y'all doing all right? It's Monday. Wait, I feel like I forgot something. Okay, yeah. Okay, so we have this idea of a local maximum, local minimum, you know, king of the hill, king of the valley, right? Little high and low points. Now you do have what's called an absolute maximum or an absolute minimum. And that would be what you think it is. That would be the absolute highest point on a graph and the absolute lowest point on a graph. if you have them, right? If you even have them, they're called absolute maximums or absolute minimums. So here are some graphs for us to look at. Let's take these 3 at a time, or we'll do these first 3. Okay, so I want to look at these first 3. So for part A, I want us to look at this one, and I'm just going to ask someone here. You see, I pretty much have gone through everyone I didn't call on last class. So, Annika, you there?
Yes. Can you hear
Okay.
me?
Yes, I can.
Okay.
Okay, so Annika, I want you to look at this graph A, right? This first one. And I
Mhm.
want you to tell me, does it have an absolute maximum? A highest point that's bigger, higher than any other point on the graph?
Would it be the 3, 6, 3, and
Yes,
6?
exactly, right? So that is it right there. So you would say, you know, at x equals 3, right? You have an absolute maximum value of 6. Do y'all understand that? At the x value of 3, you have an absolute maximum value of 6. Annika, how about absolute minimum value? Do you have a lowest point on this graph?
The 0 and 1?
Okay, so we would say at x equals what?
0.
0, you have an absolute min, right? Minimum value
Yeah,
of what?
of 1.
Of 1. Okay, that makes sense to everyone? Good job. All right, we're moving on. Let's see, Michael, you there?
Yes.
Okay. Michael, you get the hard one. This one's tricky. Okay. So for part B, start with absolute maximum value. Do you have an absolute maximum value here?
Yes.
Okay. Where does it happen?
Would it be the
At what value of x do you get a maximum value?
5?
5. Okay. And then what's the value? What's the value? What's the actual value of the function there when x is 5?
Not
So
sure.
what's the y coordinate? What's the output there?
Oh, 3?
3, right? That's how high that point is. Like that's as high as this graph ever gets, right? It gets to 3, right?
Okay.
So at x equals 5, you have an absolute maximum of 3. Understand, Michael?
Yes.
Okay. The next question, I'm going to open up to the entire class. All right. What about an absolute minimum? What do you think? Is there a lowest point on this graph?
Is it 1 because the 3 is not included?
Okay, so right here, at this point right here, I'm going to highlight a little bigger. At this point right here, we have something happening, right? But it's an open circle, right? It's an open circle. So when you think about the y value, here's the y value of 1, yes? And then Michael already said that the highest value we ever get is 3. And we actually reach 3, don't we?
Yes.
We do reach 3, everyone. We get to 3, it's a solid dot. But on the bottom, as it comes down like that, there's a hole on the bottom, isn't there? So do we actually reach 1? No, we never reach 1. Now, do we get close to 1? How close though, right? This goes back to that preliminary concept that I was talking about here, right? It's like you can get closer and closer without ever getting there. So do we actually have, where'd it go? Do we actually have a minimum, absolute minimum value here? No, we do not. We never get to 1. As much as you think, want to say, oh, the absolute minimum is 1. No, it could be, it's always gonna be a little bit more than one, and you can't tell me what number. So you're gonna say no absolute minimum here. That makes sense or no? Because of that open circle, that's why. If that were a solid dot right there, then your answer would be 1. But because it's open, you never reach it. So you don't have a lowest value. It's a weird idea. Okay, I need to move on time-wise. So what I'm going to do next is, on the next one, all I'm going to do is list the absolute max. I'm just going to tell you what the values are and the absolute minimum. So the maximum value I get here is 4. And minimum-wise, notice that it flattens out here, right? It flattens out, and that value is 1. So the lowest value I ever get is 1. Questions on that? I need to go grab the pictures here. I'm going to stick these right here. All right, so for these, on this one here, the absolute max and absolute minimum. Let's see. How about absolute max? What do y'all think? Does this have a highest value?
It would be infinity, right?
It keeps going forever, doesn't it? So our answer would be none. And the reason why is because infinity is not a number. So you can't tell me, oh, the biggest it ever gets is infinity. It would have to be a fixed number. So since it keeps going forever, there is no highest point. So we just say there is no absolute maximum. And then minimum, well, see on this, it does, right? It actually has a point there. So the smallest value you ever get is 0. Ooh, the next one's tricky again. How about absolute max? What do y'all think on this one? Does this graph have a highest point? What do y'all think? I'm seeing people shake yes and no. So none. Right? Why? You may think it's 4, but you never reach 4, do you? There's an open circle there, right? So it's that same idea where you're getting closer and closer to 4, but never getting there. So even though 4 is like, it never gets past 4, you can't tell me that has the biggest value, because you can say 3.9, 3.999, 3.9999, 3.99999, right? So there is no max, absolute max. How about minimum? That arrow means it keeps going down, right? To negative infinity. So it doesn't have a minimum, absolute minimum either, because it just keeps going down forever. So there's none here. No absolute max, no absolute minimum. Do we only have 5 minutes left? Oh my goodness. Okay. Let me just see where I am here in my notes. Yeah, I didn't even get to start talking about. So we're not going to finish this. So here's what I'd like for you to do. Just like we've done before, I want you to do as much of the homework as you can. Let me go look at it real fast to give you an idea of what can be done. And it'll be, you know, it'll still be due tomorrow night, but I will not expect, what the hell? Oh, I will not expect that you finish it all. It's okay, don't worry about it. I will extend it and I'll reopen it for you, but I want to keep you on top of things here. So let me see. So local max, local min, this is, let's see, local max, local min, local max, local min, absolute max, intercepts decreasing, odd, even, yes, 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 local max min, I think we're good there. Yeah, okay, so what number is this? Question 11. 12, 13. Okay, so of the questions that are due, I think you can do the first 10. Is that right? Yeah, you can do the first 10. All right. So don't worry about 11, 12, 13. What we'll do is we'll start class off on Wednesday and I'll finish this section up and we'll go into the next section. All right. Any questions? All right, everyone. Have a good day. I'll hang out if you have any questions.
I'll have a quick question.
Yes.
You sent the notes through an email, right? So we can access them later.
Yeah, so it's going to be a link. Go check your Canvas email. It's going to be a link. And then that link will have the files in there that you can download. And I'm actually putting them all in there right now.
Okay. Okay. Thank you.
Yeah. I'll open up. Yeah. Can you check your email and see if it's there?
Yes. Yes, I believe they are. I'm opening the link right now.
Okay. Yeah, I'm gonna go check it too, just to make sure it worked. Yeah, if you click on that, it should take you to a folder. Now they're slowly being added, so they may not be there yet. They're gonna start showing up.
Yeah, it's blanked right now, and it's nothing is loading. Oh, there it is. There it is. It just loaded right now.
You might want to refresh it, and then when you click on that, it should be like if I
It
click on
said modified a few seconds ago, so I believe it must be that one.
and they just had
Right.
the file
Yeah.
name should be the date.
Oh yes, they're all there. I can see
Yeah.
everything.
Okay, yeah,
I can see everything.
very good.
Perfect.
All righty.
All righty. Thank you,
Okay.
sir.
Yep,
You have a
you have
good
a good
one.
one.
Thank you.